flux density. All right. On the other hand, eddy current loss. So this is a time-changing flux-induced voltage within a ferromagnetic core. Okay, so the flux with respect to changing time, so will induce voltage within the ferromagnetic core. All right, and then this voltage cause swirl of current to flow within the core, and this is called the phenomenon of eddy current. All right. So here we go. This is the cross-sectional area of the core. You can see. So we have the eddy current, okay, caused by the swirl current over here, okay. And this is give a back effect to the performance of the core. So this is the unnecessary phenomenon we try to avoid, okay. If we have this solid core over here, okay, if only we have this solid core over here, so it's going to be even worse, okay. Again, so we can see this is the path of eddy current perpendicular to flux, okay. So the eddy current flowing in a swirl condition over here, okay. We have the flux flowing in this core, and it against the swirl of current, okay. Or basically we can see from here. All right, so the solid core over here again, so we have the swirl of current, so we have the flux, okay. So this is even worse, okay, here, these two. And when we come to the laminated core, this is the best solution so far, okay. So from here we are able to reduce the main problem, okay, caused by the swirl of current, okay. You can see that it's now become a very small swirl, okay, very small. So we have broken down the phenomenon into small problem, okay. Here thin sheets of soft iron also has been constructed over here in order to defy or to avoid any eddy current issue. So energy is dissipated in the form of heat because these eddy currents are flowing in a resistive material iron. Okay, this is the energy which is dissipated due to the heat and also the resistive material. So the amount of energy lost to eddy current is proportional to the size of the parts they follow within the core. So this is what I mentioned here. So the size of the parts, so they flow within the core is bigger like this. So the worse the scenario. If smaller like this, so it's much better. Okay. So in terms of the losses, okay, because it is directly proportional. Okay. So the reduced energy loss, parametric core should be broken up into small strips or elimination and build the core up out of these strips. So insulating oxide or resin is used between strips so that the current paths or eddy currents are limited to small areas. So this is the comparison. We have a solid core over here and we have the laminated magnetic core. So we have a small strip, or we separate into small pieces of strip or of core that may overcome the issue of eddy current. Okay, the blue one is the flux. Okay, so this is the eddy current or the swirl current. So unlimited core acts like a shortened turn and make a very poor transformer. Okay, we come to poor transformer application, for example, because we know that the core is the main part of a transformer, and the performance for sure become very poor. So yes, laminated core eddy current losses is smaller, restricted to smaller currents in several localized small areas. So this is much better. So now we come to the another subtopic of magnetic circuits. So another milestone. So analogies between electric and magnetic circuits. So we have over here the diagram of electric circuits consists of voltage supply, all right, I current as well as the resistance R. So we are able to come up with Ohm's law, where we have V equal to IR or I equal to V over R. Similarly, these electric circuits may be transformed or may be converted into a magnetic circuit. Okay? So we have F over here. So this is represent the magnetomotive force at the ampere turns, so as the supply. Okay, so we have the current, which is represented by phi, the flux, okay, as well as the reluctance R. Okay. Then the relationship between these three elements, where phi equal to F over R. Okay. Again, this is definition. F is a magnetomotive force, ampere turns, or we have reluctance of circuit, which is R. Okay. So this is comparable between electric circuit and magnetic circuit for you to have a common understanding between the two particular circuits, right? Okay, going into further, so we have a right hand rule over here. So we have a conductor which carry currents. So we have the direction of the orientation of the magnetic flux. So this is how we generate the magnetomotive force supply. Okay, so again, once we come to the real life, so we do have the supply E within this coil, okay, with currents flowing into n number of turns. All right. So again, the core ferromagnetic material for sure. So we have flux flowing inside, and we have MMF, the flux, where this is equal to phi F F equal to phi R. So we have the flux, we have the reluctance, and due to that, we might have a relationship between flux, okay, of phi equal to BA, and again, so we have B equal to this B, okay, equal to here, halting here, and then from here we can rearrange into this, and after we arrange, so we can simplify the equation where F is equal to 1, okay, L equal to UA. Okay, so sorry, not this one. So we have F equal here and I, and this mu A over L is actually here. Okay, so by having this, we can further simplify the equation into R. Okay, R, which is L over mu A. Okay, here. So in series and in parallel. Okay, Req, the equivalent reluctance in series. So just like we have, just like what we have in the electric circuits. So the resistance in series. So we do have same here, R1 plus R2 plus R3. So reluctance in parallel, 1 over Req, the equivalent R equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus blah, 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 blah. Okay. All right, now we come to example number 1. So a ferromagnetic has 3 sides of this core are of uniform width. So the width is uniform for all the 3 sides or all the 3 legs of core, while the fourth sides, so the fourth leg is somewhat thinner, okay, smaller size. So the depth of the core is 10 centimeter, and the other dimension is shown in the figure. So there is a 200 turn coil right around the left side of the core. So this is n number of turns. So wrap around the left side of the core, assuming the relative permeability mu R of the ferromagnetic core is 2500. So this is the permeability, the relative permeability mu R of the core. So how much A flux will be produced by 1 ampere input current, and B flux will be produced by 3A input current. So we are going to find out the value of flux if 1 ampere of current is being injected, as well as 3 ampere current is being injected. So the solution, 3 sides of core have the same cross-sectional area, while the fourth side has a different area. So that's the core can be divided into 2 regions. So basically, this is the figure or the diagram of ferromagnetic core in example 1. So the 3 legs with uniform width, is over here. So lake number 1, so we have here lake number 1, for example. And so we have lake number 2, and we have lake number 3. So this is what the question described earlier. Okay, but somewhat lake number 4, the fourth side or the fourth lake is somewhat thinner here. So this is for the fourth lake of the core. Okay, 4. Okay, you see this is the uniform width, which is 15 centimeter. So we have another 15 centimeter. So we have 10 centimeter width of the fourth leg. Okay, here also similar, the third leg 15 centimeter. So the single thinner side, so the other 3 sides taken together. So the magnetic field circuit corresponding to this core is shown in figure 2. The mean path length of region 1 is 45 centimeter, and the cross-sectional area is 100 centimeter square. So we start with the different one, okay, because we have the one different size of core, the fourth one here. So this is somewhat thinner or smaller. So we are going to calculate the mean path length here over here. Okay, the mean path length L of leg 1. Alright, so this leg 1 or leg number 4. So basically we start from the middle. Alright, so let me change the color into a blue color. So we start with the middle here and here. Alright, so we have along this line is 30 centimeter. Okay, so this is again how to calculate the mean path length of this leg, okay, the fourth leg. And then we have 30 centimeter over here. So we have this point up to this point, which is 7.5. So how to know? Because I have 15 centimeter over here, which divided by 2. Okay, because I take from middle. Okay, so it's going to be 7.5 centimeter. So identically, so we have 15 centimeter, the width for this line or this area. Okay, so divided by 2. Okay, so we have here divided by 2. This is equal to 7.5. Okay, 7.5 centimeter. So 7.5 plus 30 plus 7.5, another 7.5. So the mean path length for the first leg, okay, the thinner or the smaller leg. So this is equal to 45 centimeter. Okay, and then the cross-sectional area is 100 centimeter square. So the area equal to width multiply or times depth. The width is 10 centimeter. All right, so this is the width of the first leg. Okay, so this is 10 centimeter. Okay, multiply by the depth. Okay, the depth into the page. So we have, let's say, I draw it in 3D. So we have the depth, and I try to color it, okay, or to mark it, something like this. Okay, so the depth is 10 centimeter over here. So it is given over here, 10, depth is 10 centimeter. So the width is 10, and then the depth is another 10 centimeter, multiply both of them. So you may get 100 centimeter square. So we have done with the L, the mean path length, as well as the A for the smaller leg or smaller side. Okay, and thus the reluctance in the first region, okay, R1. So here this is the L1 or R1. This is region, the blue one is R1, region 1. Okay, so is R1 equal to, okay, this is back to our previous equation, L1 equal to mu A1, so L1 over 2. So expand the equation, so because we know that mu equal to mu R mu naught. Okay, so substitute into here, and then we have A1. Okay, so L1 45 centimeter, convert to meter, which is 0.45 meter. So 2400 is the mu R, the relative permeability given in the equation here, 2500. Okay, and then we have 4 pi times 10 to the power of -7. So this is a constant value of air permeability or free space permeability mu naught. Okay, and 0.01 is A1 in meter. Okay, so we have 0.01 meter. This is taken from 100 centimeters square. So when you come or you convert to meter, so you might get 0.01 meter square. Okay, so don't forget to convert everything to meter as the SI unit. Okay, and then R1 give 14,300 ampere per Weber. So the mean sparse length of region 2 is 130 centimeter and the cross-sectional area is 150 centimeter squared. Okay, similarly, if you go back to your figure over here, so let me again change the color into the yellow or the orange. Never mind, or maybe the green color is much better. So which one? Okay, this one. So we have done this region number 1. Okay, now we move on to region number 2. Region number 2 cover all these remaining 3 lakes. Okay, the one I color in green. All right. So green means region number 2. Okay. So because all of them are having the uniform width as well as the uniform depth. Depth is 10 centimeter. Okay, the width is 15 centimeter here. You can see 15 centimeter. So we have another width of the second leg. Okay, it is 15 centimeter. So we have 15 centimeter. Of course, here 15, 15, and here also 15. Okay, so we start again to calculate the mean sparse length, the L. So now we try to calculate L2. Okay, L2 consists of all here. Okay, here down to here, down to here, up here. Okay? We have done the blue color, so don't go over that again. So try to focus on the green one. Okay, where to start? Of course, in the middle of leg 1 of region 2. So leg 2 of region 2. Okay, you can see it is moving. So and then middle of leg number 3. Okay, the L, the mean sparse length. So again, from all here, we know this is 30 centimeter. So add 5 centimeter more over here. Okay, because you know this is 10 divided by 2. This means from this point to here is 5 centimeter. Here to here is 30 centimeter. Sorry, I didn't write the centimeter. So just write the number. So here to here, middle. Remember the middle. So this is another 7.5. How I know? So just divide 2 from here. Okay. So 15 centimeter by divide by 2. So down here, so we have 15. This is actually 15. Okay, so divided by 2, so we should have another 7.5. Okay, then along this line, we have here same. All right, 30. So this is 30. So up here, okay. And then down here, we have 15 divided by 2, we have 7.5. Then here, we have 15 over here, divided by 2, so we have 7.5. Here along this way, we have 30 centimeter. And here we have 5 divided by 2, so we have 5 centimeter over here. Okay, 5 centimeter. So you just need to, okay, let me circle 5, 30, so 7.5, 7.5, 30, so 7.5, 7.5, 35, you add up to together, all together, give you the mean sparse length of region 2 is now 130 centimeter or 0.1, oh, sorry, 1.3 meter. Okay. So and the cross sectional area is 150 centimeter square. So we already know the depth. Okay, depth is 10. So now we need to figure out what is the width. Okay, it's actually 15. Okay, this is actually 15. Apparently, you can see from here, this is 15, this is 15, and it is also stated in the question that the widths are all uniform for the 3 legs or the 3 sides. 15, 15, multiply the depths here, 10 centimeter give you the area. Okay, so multiply these two. So this is actually your area, 150 centimeter square. Don't forget to convert into SI unit, 0.015 meter square. So into this equation, R2 equal to L2 over mu A2, expand again the equation, mu equal to mu R mu O. So mu R is given in equation 2500 and mu O is a fixed constant 4 pi multiplied by 10 to the power of minus 7, and L2 is the mean flux link. The total L2 we just calculate, okay, 1.3 meter, and this is the area of the cross sectional. Okay, of the core, cross-section of the core, which is 0.015 meter square. Solving this, R2 give you 27,600 ampere turns per Weber. And from there, we might calculate the total reactance. This is really symbol of equal, right? Not negative. Okay, so RT equal to, or REQ equal to R1 plus R2. So plus sum up, we have 41,900 ampere turns per Weber. So the method multi-force MMF, the F is Ni 200. So this is number of turn. So this is the ampere current 1. So this is giving us 200 ampere turns. So to answer question A, the total flux in the core produced by 1 ampere input current is, so flux over F over RT, so we have 200 from here. So since we have calculated the current, the amount of 1 ampere, so just straight away use this value into here, and we have the total reluctance, which is 41,900, and giving the flux, the total flux in the core produced by 1 ampere is 0.0048 Weber. And then similarly for question B, total flux produced by 3 ampere input current, so back to F equal to Ni. So we have number of turn 200, we have I 3 ampere 600, and 600 into here F over RT. So the same value of RT. So giving phi equal to 0.014 Weber. All right, thank you very much for your time, and thank you very much for watching. So we will continue in the next slides in the coming video. So again, thank you very much. Have a nice day.